Welcome everybody tonight to the February RASC Edmonton Center public meeting, and we'll get started. I got some information last night that was the other night quite interesting. That in a single drop of water, there are more atoms in that than there are stars in our solar system. Now, I got not only was I debunked that initially. The key word in their solar system. So there's more hydrogen atoms and stars in our solar system, which yes, you have to agree with. But then, of course, if you don't think solar system, you're thinking galaxy or universe. Of course, then you start questioning that theory. But anyway, after clarifying it with the original sender of the text message, I was able to understand fully what he meant. Okay, the January 2026 meeting minutes are available on the members area of our website. Has there any errors or omissions? No, good. So if I can get a motion to have those minutes accepted as posted.
I'll make that motion.
Oh, that sounded like Tom.
It is Tom.
Okay, I thought you'd be speaking Spanish by now. We wouldn't want no Tom down in Mexico. So, do I have a seconder? Kent Martin, second that. Okay, all in favor, raise your hand. Any opposed? Carried. Okay. Tom's in Mexico, so Jeff Whiten, he's down there as well. So our treasurer asked me to talk about the treasurer's report a little bit. I'm far from being a financial wizard or a treasurer, so I will see what I can come up with here. Okay, so basically the starting balance for the general account was $79,986.36, and we ended the month at $83,595.67. The credits were primarily due to memberships, about $1,063, calendar sales, GFT rebate, and there were no expenses that hit that account in January. Starting balance for the casino account, $67,109.05, ended the month at $58,062.87. Expenses largely attributed to the CubeSat donation of $1,000, Planewave $4,465, and a BNLO operations at $3,551. The Bob Drew Telescope Fund, the fund was set up from a $25,000 donation from Bob Drew to support the development of the UDT. Current balance is $1,227.06, unchanged from December. So I think that's about the width of my knowledge on on what we're doing here. We do have a casino coming up in June, so that should get our casino account back up. And I think Lucas had a few spots left available. So if you've seen his email and you have time to volunteer, please get a hold of Luca. Okay. Our guest speaker tonight, I'm going to have Sharon Morsink come up and introduce our guest speaker, and we'll go from there.
Thank you very much. I'm very happy to introduce Dr. Craig Heinke, who will be giving today's talk. Craig Heinke's, I was kind of shocked to realize that he came here in 2008, which means that we should be starting to plan his 20th anniversary in Edmonton party, I think, pretty soon. So he came here in 2008, and by strange coincidence, this is the same year that the Fermi Gamma Ray Telescope was launched. Coincidence? We think not. Okay, and Craig is an expert on lots of things that come together, so very interesting ways. So he studies neutron stars, white dwarf stars. He studied a number of black holes, including the one at the center of our galaxy, although I suspect that's not what he's talking about today. He's also an expert on globular clusters and star systems in general. So anyways, so please come on up. Thanks, Sharon.
So let's see here. Okay. So I'm going to talk about the nature of gamma ray emissions, nature of gamma rays from the galactic center, which is a little different from my normal spiel, which is normally about X-rays and globular clusters. But I'm going to wind up talking about X-rays and globular clusters anyway because I love them. So let's go on and just so briefly here we got the electromagnetic spectrum. Just to remind you that we've got our optical light here and ultraviolet, X-rays, and gamma rays. And these are our high energy stuff from things that are extremely hot. And actually, gamma rays come from things that if you have something that's hot enough that it would emit gamma rays like a black body, it will generally emit all its heat very quickly and cool down. So usually you have things emitting gamma rays have to be something special, something where particles are being accelerated to really, really extreme energies. And so there's some possibilities for that I'll mention. And then you dip down the other end, you get infrared, microwave, and radio emission. And there's cool ways we can see things, very high energy objects in the radio spectrum as well. So it's nice to be able to poke around in other parts of the electromagnetic spectrum and see things that you can't see in the visible and ultraviolet, like the center of our galaxy. So we'll flip around through here. I'm going to show you some pictures of the Milky Way in different parts of the electromagnetic spectrum. So this is the Milky Way as seen in visible light if you could look all the way around, right, all at once. So this is projected, it's a Mollweim projection or something, right? So this is photos by Axel Mellinger strung together. So here's the center of the galaxy, the disk of the galaxy, the bulge of it. Here's the Magellanic Clouds, which are sadly not visible from Edmonton. But so the center of our galaxy is hidden behind a lot of dust clouds, and so we can't see it in the optical. But if we go to other wavelengths of light, we can see stuff throughout the Milky Way. And so I won't go through all of these in detail, but in the near infrared, you can see stars throughout. Here's our optical line. This is just the plane of our galaxy. And you'll see the gamma ray down here. And the X-ray, we can kind of see, it depends on which parts of the X-ray. You can kind of see into the center in some regions. So I want to focus on the gamma rays. So this is the Fermi Gamma Ray Observatory, which was launched in 2008 and scans the whole sky. So there's a table, right? So you can get a sense of how big it is. And so what it does is basically gamma rays come in, and the gamma ray is energetic enough that when it strikes one of these kind of foil plates, it creates a pair, a positron and electron pair that then pass along through here. And so you can detect them passing through these different foils, and then they land down here in this calorimeter, which basically calculates the total amount of energy that's deposited down there. So it's very different from the kinds of telescopes that we're used to with optical or even X-rays, where you kind of focus something. You can't focus gamma rays. You just have to kind of track them and hope that you get a sense from measuring these kind of things down here, roughly where on the sky it comes from. So Fermi is the best gamma ray telescope that's flown yet. There have been several others that NASA and other space agencies have flown, but Fermi is the best so far. And here's its view of the sky as of like the first 10 years or so. And so let's go through and look at what it is that we're seeing here. So one thing that we can see in the gamma rays is a bunch of supernova remnants. So these are the remnants of exploded stars. And so they're, as the material flows outwards, it makes a shock because the stuff is traveling very, very fast at maybe 10,000 kilometers a second initially or so. And so as it runs into the interstellar medium, it makes a very strong shock. And that shock is capable of accelerating particles as they pass back and forth across it up to a significant fraction, well, even up to very close to the speed of light. And so these particles then are what we call cosmic rays. They're extremely energetic. And they then, you can see evidence from them by them emitting gamma rays that we can see from, among other things, radio emission, X-ray emission, all kinds of stuff from the edges of these. And so that's one thing that produces gamma rays. And another feature is that they accelerate these cosmic rays, and then these cosmic rays may wander out of the supernova remnant and wander through the galaxy. And if they run into, say, atoms in some molecular cloud, and I think that's the next slide here. Yeah, okay. Here's the how they. Let me point at this one, because most of you are not sitting over here. So if I point at this one, then you can kind of see what I'm doing, right? And feel free to raise your hand or just ask a question out loud, because I might not see you because you're all in darkness. So the idea is that the particles might, as they bounce back and forth across the shock, they get a slight energy boost each time. And so that raises their energy to the point where then they finally wander off and proceed throughout the galaxy and deposit their energy somewhere else. And if one of these cosmic rays then comes upon some other piece of gas somewhere else in the galaxy, a proton in a molecular cloud or something, it can liberate multiple subatomic particles that then might decay and produce gamma rays. And so if we look at the, I've lost my laser, but look at down at the bottom is our gamma ray image of the galaxy, and just above it is an image of the galaxy in molecular hydrogen along the plane of the galaxy. And you see these look kind of similar. There's some individual dots in the gamma ray thing that aren't reproduced in the molecular hydrogen one, but overall they look kind of similar because a lot of these gamma rays are produced by these cosmic rays striking these molecular clouds and liberating gamma rays that then come out and we see. Now, does this still work? No, I think the batteries might be totally dead in this. Let me see if it's possible to get new batteries. I don't know. I'm going the wrong way. I just switched to this. I just dropped this thing on the ground. Here you go. Okay. So let's see if this works.
It just probably just got loose.
Is it working now? Okay. All right.
Yep.
That's my fault then.
That's a laser pointer too. Use it.
Okay. Right. Thank you. All right. User error. Well, I'm used to that. Okay. Right. Let's see. Where was I? Let me back up. Okay. So we were talking about molecular clouds, and then we go on to other things that we can see in the gamma ray sky. So another thing we can see is gamma rays from radio pulsars. So the idea of a pulsar is you have a neutron star. So that's the condensed core of a massive star that's gone to supernova, and its core has collapsed down to be mostly made of neutrons. And many of them are spinning very quickly and have strong magnetic fields. And that generates then a very strong, if you have a strong magnetic field spinning around very fast, it generates a very strong electric field, which accelerates particles. And then they're forced to kind of go around the magnetic field lines. And as they do so, they do complicated physics, which produces radio emission coming out from above the magnetic poles. And as the thing is rotating around this line here, the radio emission going out this way kind of sweeps around the sky. And so we can sometimes be in the line of that. And so we see a radio emission every time it sweeps across our line of sight. And so this is the concept of a radio pulsar. In addition to the radio emission, they also produce gamma rays from the accelerated particles moving around their magnetic field. And these are of a somewhat different format than the radio emission, and we can kind of figure out where this comes from. We actually understand the gamma ray better than we understand the radio emission from radio pulsars. And so if you look on this image, there's a whole bunch of individual dots we see, and many of these are radio pulsars. In fact, Fermi has been great at identifying radio pulsars before we actually see the radio pulses from it. We see a gamma ray source and we point a radio telescope at it, and then eventually we're able to spot, there's radio pulsations, which we just look hard enough for it. So Fermi has been fantastic for finding pulsars. But it can't see all of them in our galaxy. It's not sensitive enough to do that. And then another thing that we can see with Fermi is gamma rays coming from accretion onto black holes in distant galaxies. So this is a nice example. This is an optical image with Hubble of M87. So it's an elliptical galaxy, which is up here somewhere, where we see the core of the galaxy right here has a supermassive black hole in it. And that black hole, as it is consuming matter, some of the matter, instead of falling into the black hole, gets ejected out via this jet that you see here. And people saw that over 100 years ago and were like, I don't know what's going on with with that. It took us a long time to realize, oh, these were giant black holes eating stuff. So who knows what things we see in our images today, we have no idea what's going on. And 100 years from now, people will say, oh, of course, that's this and that strange thing. So there's obviously a lot of these guys on the Fermi sky. Now, the key thing that I want to talk about is the fact that when we account for all these various different kinds of things I've explained so far, and we say, okay, where's this gamma ray emission coming from? We end up with a spot that we don't explain. And so basically we can say, okay, we take the Fermi emission and we subtract off our model for where the molecular clouds are. And we're left with a big blob at the center, which we can't explain. And so if you plot out in angle away from the galactic center, so this is 0 degrees, 1 degree, 2 degrees from the galactic center, and you have a number of gamma ray events per square degree, right? You can say, okay, how much would we expect if we had the disk and the bulge of our galaxy? And you have this line here. And you said, what if you put a single point source in? Well, it wouldn't be just a point in Fermi's vision, because Fermi kind of is blurry vision. So it would kind of look like that. And those together wouldn't account for it. So you say, what if I add in another component that has a different kind of distribution with angle? And you can replicate these dots, these little lines here with the error bars are the actual observations from Fermi. And so if you combine the disk and bulge predictions from our galaxy plus some other component that's labeled DM here, which you might guess is for dark matter. It doesn't have to be dark matter, but that's one distribution that will work. You can replicate this distribution. So that's obviously very exciting. So what's going on with that? So the concept here, is that one explanation for this extra gamma ray excess at the galactic center is from dark matter annihilation. So we don't know what dark matter is, but the leading candidate at the moment is something called weakly interacting massive particles, meaning they're things that are more massive than protons and that don't interact with by electromagnetic radiation in any way. They interact via gravity, and maybe they interact via, say, the weak nuclear force. They might interact with each other, possibly. And if they do, they might, like if you have two of these things, put the I there to replicate these guys. So you got like time going this way, kind of. If they interact together, they might produce other products, and they've got a whole bunch of, these are quarks or W bosons or things, which then break down into other things, maybe neutrinos or antimatter or gamma rays, all kinds of stuff. So you might be able to see these things, any of these kind of things, as products if dark matter annihilates with itself. So dark matter would annihilate with itself more frequently at the places where there's the most dark matter. That's the basic concept. And the dark matter will be densest at the center of our galaxy. So you might expect then to see dark matter annihilation coming from the center of our galaxy. So this is the spectrum. So this is energy versus flux per energy bin, essentially, that we see. Again, these kind of lines here from Fermi. And this is suggested possibilities for what you might see if dark matter annihilates with itself. And they've got different ideas here for what it might annihilate into. It might annihilate into charmed and anti-charmed quarks, or into tau and anti-tau leptons, which are kind of like electrons but more massive. And either of them give you these kind of distributions which are kind of close to what we see from the Fermi actual observations. So that's fascinating. It means that the spectrum of energy that we see could be consistent with dark matter annihilation. And I've just seen in the previous slide that this one back here, that the distribution, the distribution in space is also kind of consistent with dark matter. So that's very interesting. And people have gotten very excited about the possibility, because when we look at dark matter, we have all kinds of evidence for it from looking at the gravitational effects, and we have some kind of indirect evidence from looking back at the early universe and looking at its impact upon the cosmic microwave background, but we haven't seen direct evidence of, say, dark matter particles interacting with our detectors or dark matter particles annihilating somewhere else, right? Now, we might say, but if you see it in the galactic center, maybe you should see in other places too. Like you could look at other nearby galaxies. And so this is constraints upon dwarf galaxies near our own. And so these are the kind of plots that the particle physicists like, of plotting dark matter mass, because you don't know the mass of the dark matter particle, versus its cross section, right? How likely is it to interact with normal matter? And so these are different predictions. If you say, okay, if we say that the stuff in the galactic center is dark matter annihilation, then we should predict a particular, say, mass and cross-section for it. And then we can kind of test that by looking at nearby dwarf galaxies. And these are two different possibilities for what it is. If it's decaying through these beauty quarks and anti-beauty quarks versus tau and anti-tau leptons, right? What you would get. And this is the constraints that we have from looking at these nearby dwarf galaxies. And so this constraint here seems to maybe rule out all the things above it would be ruled out. And so maybe it would rule out these guys. But then you say, oh, what about if it decays into tau leptons? Then it's still maybe consistent here. But the takeaway message here, I think, is that we aren't seeing any evidence of dark matter annihilation from these dwarf galaxies. And it's starting to get a little bit suspicious that you think maybe we should be seeing something if the stuff at the galactic center is actually dark matter annihilation. It's not proven yet, but it's kind of, maybe you might see it pretty soon. Maybe if Fermi goes another 10 years, maybe they will see it. We can also look at the evidence from people running giant dark matter detection experiments underground. And they're looking to see, do we see dark matter interacting with xenon nuclei and such? And so here's mass versus cross-section. This is a result that's from this past year with the Lux Zeppelin experiment underground in a mine in South Dakota, 7 tons of xenon. So it's the kind of thing where you're like, okay, this is a very expensive experiment. And so they've gone very deep, and it's going to be really difficult to move it another factor of 10, right? You can make 7 tons of xenon, but can you get 70 tons of xenon? That's kind of hard to instrument that. Anyway, they've pushed it down to this level down here. Now, these kind of regions here are various different theoretical predictions of where the dark matter particle might be. And so they're ruled out a big chunk of space, but there's still space down here. What is this gray thing down here? Well, this is what we call the neutrino floor. It's where neutrinos coming from elsewhere in the universe, including our own sun, are going, mostly our own sun, are going to be polluting the detection. So when they push the dark matter limits down into this region here, they're going to be getting detections which aren't dark matter particles, but are neutrinos, which are less interesting because we think we kind of understand neutrinos. We don't understand dark matter at all. It just makes it a little bit harder. If you know you're looking for the sun, then you have to be directional dependent and say, okay, look away from the sun. But anyway, all I'm really saying with this is, it's just, so far we haven't found anything, and they've probed through a lot of space where they hoped they might. It's been a long journey. And this is just showing here how much the cross-section has gone by year. They've been moving very fast, actually. So they say the Moore's law for dark matter searches, they do a factor of 2 every 1.5 years, which is beating Moore's law for computers, which is a factor of 2 every 2 years. And I thought that was a really cool thing to show. They've worked really hard. Okay, so dark matter would be really cool. We don't yet have any other detections of it. Are there any other options to explain it? And there is. And the other principal explanation people have suggested is millisecond pulsars. So what is a millisecond pulsar? I've described what a pulsar is. It's this fast-spinning neutron star. Millisecond pulsars are like these, but they're recycled, meaning that it's a neutron star where it was born as a pulsar, and then it kind of slowed down and turned off, and then something has caused it to turn back on again. The idea is these illustrations here are two different paths to go at. So this one is going along its kind of history like this. And then there's another path I'll talk about in a moment. So the idea is you have a binary with two stars. One of them blows up, makes a supernova, right? And you've got another star in it. And then this other star starts transferring mass. So here's the other star transferring mass onto the neutron star. And that spins it up until it's spinning at hundreds of hertz, hundreds of times a second. And then at some point it will turn on as a pulsar, and then the complicated physics that are going on then involve a wind that blows out of relativistic particles that will then eat away some of the companion star, perhaps. And so now we've got something that spins very fast. It's a very old neutron star. It'll live for billions of years like this. It has a lower magnetic field and slows down slowly. The other way you can get these guys, and I have to talk about this because it's globular clusters and I love globular clusters, is that maybe you have a binary star and you have a neutron star coming along, and the neutron star can kind of exchange into this. So globular clusters are really cool because they're so dense. One of the reasons they're so cool. And so that means that in our neck of the woods around the sun, the density of stars is like 0.1 stars per cubic parsec. But in a globular cluster, it's like 1,000,000 stars per cubic parsec in the denser ones. So that means that the probability of your star actually interacting with another star is quite large. And especially if you're in a binary star, you might have another star come along and steal your partner. So then you end up with a neutron star and another star in an orbit where before it was two normal stars and the neutron star was alone. Why is that important? Because when a large star goes supernova, usually if it was in a binary, it wanders off from its binary because the supernova explosion tends to unbind the binary. So you're more likely to generate millisecond pulsars in globular clusters than in the field. And so this is a great place to look for them. Okay, so here's kind of what millisecond pulsars look like in globular clusters if you like to look in X-rays like I do. So this is the globular cluster 47 Tuc as seen in X-rays. Here's all these various X-ray sources in there, which are neutron stars and black holes and white dwarfs and all kinds of stuff. And these little diamonds here are showing you where the millisecond pulsars are. And most of them are relatively faint. You can kind of just vaguely see them in here as compared to other X-ray sources there. So millisecond pulsars, among other things, are gamma ray bright. And so this is plotting the pulse phase in radio of a millisecond pulsar. So there's the bright peak, and here's the second peak on it. And this is in gamma ray. And you see they don't line up. They're coming from different places around the neutron star. But nevertheless, it's strongly pulsed with the same period. And then you can make a spectrum of it, too, separate out by energy. And what we're looking at here is not actually a single pulsar. It's a whole bunch of pulsars in the globular cluster 47 Tuc, the same one I showed you a moment ago there in X-rays, but this is in gamma rays, and this is M62. So they have a characteristic spectral shape in gamma rays. So the fascinating thing is that the spectrum of millisecond pulsars in globular clusters kind of matches that in the galactic center. If you look at normal pulsars, they don't quite match as well, but the millisecond pulsars match. And the galactic center thing is kind of spread around like the old stars in the center of our galaxy, which now I think about it is my next plot. Yeah, here we go. Right. So this is the Fermi gamma rays are the color here, and the contours are kind of where the stars are located in their galactic bulge, and they kind of match. So that's kind of cool. So you'd say, okay, what would you need to explain this? So this is kind of a plot of our galaxy in X and Z, right? So think of the plane of our galaxy is along here. Here's the center of it. And so the idea is this is kind of like the distribution of stars. Here's known millisecond pulsars plotted in this. And then here's where the bulge millisecond pulsars would have to be in the numbers. You need about 10,000 or 40,000 maybe to explain the gamma ray emission that we see. So that could work. You need to have quite a lot of them, but it could work. Now, this is the center part of our galaxy as seen in the radio. And there's all kinds of complicated things going on here. Here's supernova remnants. I think this is an H2 region, so massive stars ionizing the region. There's weird things which we don't understand. There's a lot of stuff going on. And what I'm showing you, what I want to show you here is just that it's really weird and chaotic, and there's lots of ionized gas floating around, and it makes it hard, actually, to see millisecond pulsars through all this. Why is that? Well, if you look through ionized gas, if you have, say, electromagnetic rays going through ionized gas, they will be scattered. And that has this effect that you can kind of see by looking at these. So these are pulsars, as seen, looking close to the galactic center. And these are not millisecond pulsar. This is a 1.1 second pulsar and a 1.5 second pulsar. But what you can see is that as you go from high frequencies, 9 gigahertz, down to 1.5 gigahertz, it gets scattered more. There's scattering properties of this material between us and the galactic center that kind of smear out the pulse. And it smears out the pulse by a certain time scale. Now, these guys are like 1 second pulsars. So if you're trying to observe down here and look for millisecond pulsars, they're spinning, something like 30 or something times faster. When I say millisecond, they're not at exactly 1 millisecond. They're at like 10 milliseconds or 3 milliseconds. But still, that means that, if you're spread out this much, that timescale is much more than the timescales, the spin periods of these millisecond pulsars. So you'd be entirely blurred out from one spin to the next, and you wouldn't be able to see them. This is another way of showing that information. So this is showing the periods and radioluminosities of known pulsars that we have in our neck of the woods, as if they were at the galactic center, and what would we be able to see? And these are different observations they have. And here's normal pulsars, and here's millisecond pulsars. And you see these sensitivity curves turn up here, so we can see things up there. And so it says that basically because of this scattering, we can't see the fast spinning pulsars so well. And these guys are kind of faint too. So we are currently unable to detect if there were a whole bunch of millisecond pulsars in the galactic center. We can't see them with the telescopes we have at the moment. Now, this is operating at, a few gigahertz here, and you think, okay, well, you know what? This gets sharp if I go to higher frequencies. So you say, maybe I just go to higher radio frequencies. And so we have telescopes that can do that, such as ALMA, for instance. ALMA, I'll come to this in a second. ALMA is a high-frequency radio observatory in South America, and it operates at very high frequencies, and so it doesn't have a problem. Things are just straight across. It's not having a lot of problems with scattering at low frequencies, but it's not very sensitive because pulsars have less emission at high frequencies than at low frequencies. So even though ALMA is a really powerful telescope, it can't probe very far into the galactic center just because the pulsars are so faint. So what's the solution? So one solution for this is to say, well, let's build a really big radio telescope. So let's build one with a square kilometer of collecting area. So it's called the Square Kilometer Array. And it's a radio telescope that a bunch of nations, including Canada, but the rest are largely in Europe and Australia and South Africa, are building actually in two parts, one in South Africa, one in Australia. And so phase one of that, kind of the first version, it's actually not a square kilometer, but it's a lot. It's really big. Will be complete in about 2032. Okay, so, I could pause my talk here and we could come back in 2032 and keep going. But instead, let's talk about another thing we might be able to do that might get us a little bit faster, something in this direction. We won't solve the mystery completely, but we'll get a step towards it. Are there any other ways we have to target the millisecond pulsars? We have some problems with the radio, right? The dust obscures in the optical and UV. Gamma ray telescopes have really poor angular resolution. So although we can tell there's a big blob, we can't actually resolve it into individual pulsars. I mentioned the scattering in the radio. What about an X-ray? Well, so I showed you actually that millisecond pulsars do radiate in the X-ray, and I love X-rays. I'm an X-ray guy, so I really want to poke at this some more. Right? So most of them are very faint in the X-ray, and the spectra are mostly low energy where the dust absorbs. But there's a small fraction of millisecond pulsars that are brighter and produce higher energy X-ray photons. So how many of those are there? So we can look at the millisecond pulsars we see in globular clusters. And I put a little red arrow here pointing at this one that's a little brighter than all the rest of them. So what we can do is we can say, okay, most of the millisecond pulsars are just radiating emission from the hot star's surface. And those ones, which are like all these guys, the faint ones, couldn't be seen if you put them in the distance of the galactic center. They would just be obscured by the dust. But in some, like this guy, you have a companion, there's a stellar wind coming from the companion that strikes the pulsar's wind and makes a shock, and that shock accelerates particles and they radiate in X-rays as well as gamma rays. And so we can actually see those. And so those are bright enough in the X-rays, you might be able to see them even at the galactic center. And so this is some work that my grad student, Jake Zhao, did, and he just graduated this past year. And so I was like, oh, let's show off some of his work. We were able to make a histogram of the luminosity of millisecond pulsars in globular clusters. We looked at 36 different globular clusters, and this is kind of our histogram. So this is luminosity in our CG, our weird SI-based sort of units called ergs per second, right? So there's a few bright ones and then a lot of faint ones, right? And we can extrapolate, there's about 1,000 millisecond pulsars altogether in the 36 globular clusters we studied. Most of them are very faint. These are upper limits as well. We can apply this to the galactic bulge and say if there are 10,000 pulsars in the galactic bulge, then we predict there should be 1 to 90 millisecond pulsars with an X-ray luminosity above 10 to the 33. It's a big error bar because we're going from one source, so it's kind of hard. But if you go down to 10 to the 32, we have a few more, and so we can say, say 20 to 900 with the X-ray luminosity above here. And so looking in the right part, if there's enough X-ray data, you could actually find these guys. So if we look at the galactic center in X-rays, this is kind of a wide-scale view of this region, which again is crowded and weird and all kinds of stuff. And then this is zooming in on this part here. You can see this is a supernova remnant, and then there's all these individual point sources around there. So we can see lots of X-ray sources here. There's thousands of X-ray sources in the direction of the galactic center, including at the energy ranges we're talking about. But most of these are what we call cataclysmic variables. They're accreting white dwarfs, we think. There's some accreting black holes, accreting neutron stars. There's distant galaxies behind our galaxy and all kinds of different stuff. How do we figure out which of these might be millisecond pulsars? I mean, I can just say some of them could be, but that's not very interesting. So this is work by another of my graduate students who also is just graduating, Pavan Hebar. So we can look at the spectra. So if we spread out the energy of the X-rays coming from different sources, we see differences in them, and particularly differences we can use. So this is the spectrum that we see from objects in the galactic center, and I'll draw your attention to this here. This is a big emission line from iron. And so that's telling you that there's gas in there that has iron in it, where the iron still has some electrons, and an electron falls from one energy level to another in the iron, and that can produce this line here at a particular energy that we can see. Whereas the millisecond pulsars, on the other hand, this blue here is what their expected average spectra is. Basically, in the magnetosphere of the millisecond pulsar, all of the iron gets all of its electrons stripped off, and the emission we're seeing is not just from hot gas, but from synchrotron radiation, and so we don't see this line. So that says this is a way we can distinguish the cataclysmic variables, which we don't want to look at, from the millisecond pulsars, which we do. There are some other things that don't show iron. There's X-ray binaries, which probably should be fewer of those in millisecond pulsars. There's some background galaxies. We can kind of predict how many of them there should be, because we see them in other parts of the sky. So here's a this is the most complicated plot, or plots. So I'll start with the simulations here. So we define a ratio of the X-rays in this line. So if I back up here, right? The X-rays, they're coming in this line versus the X-rays on either side. So we can kind of see, okay, I'm making a ratio of, if it's high, then there's more of a line. And so that's what this ratio is on this axis here. And then this axis here is the total number of counts that we're seeing from it. So if you have millisecond pulsars, it's close to 1 on this ratio, meaning that there's not extra emission from this line. But if you take these cataclysmic variables, the ratio is higher. And if you have a lot of counts, you can see that. And so these look different in the shape. And this kind of encloses, I think, 90% of the total simulated plots, right? We can count for shot noise, essentially, is how wide these are spread out down at low number of counts. And then we can take these kind of plots here that will show you where most of the CVs should be and where most of the millisecond pulsars should be. And we can compare them to the observed sources over here on the right. And so if you look at this here, so here's our CVs, and so you see, okay, the CVs should be mostly within here, and that's fine. There are a bunch of things that kind of look like they're in this region, but there's also some things that don't match up where these guys are. And if you look at the simulated millisecond pulsars, all these are aligned with that. Now, they could also be, and the very bright ones actually are going to be X-ray binaries, but some of these guys down here could well be millisecond pulsars and aren't explained well by this. So we can do some kind of funny statistics and figure out, roughly how many we're talking about. And we get some numbers. We see that we have two X-ray telescopes we're looking with. One is XMM, the other is Chandra. We get 54 from one and 83 from the other. And some of these already have a known nature. The bright ones are X-ray binaries. There's some things that are young pulsars and other stuff. There's probably some guys or cataclysmic variables that have snuck in there anyway. And some of them are background galaxies. We can estimate how many there are. But we're left with about 20 candidates from XMM and 60 from Chandra that could be millisecond pulsars. So, okay, that's okay. That's good. Does this match with what we expect to explain the gamma rays? So we can go and figure out if the gamma rays are all from millisecond pulsars. We can say, okay, what's the typical millisecond pulsars gamma ray emission, and how many of them are in the areas we studied with, and so on. And you can figure out that you predict about 20 to 80 millisecond pulsars should be detected with Chandra, and we see 60 candidates with Chandra. So it kind of matches, right? The numbers are better than we expected when we were starting this program. We were like, oh, we didn't know if this is going to come out at all. We didn't know if we detect anything that would be plausible, and it actually kind of works. That's fantastic. Now, I have to say, it's hard to verify the nature of these X-ray sources because they're hidden behind all this dust and gas. We can't look at them in the optical. You could maybe go with the infrared and try to figure them out, and you can do deep radial pulsation searches. So there are ways we can stab at them, but it's not going to be really easy. It's going to take some work, but it would be really fun if we could verify these are millisecond pulsars, or if we could verify that none of them are millisecond pulsars, and then you'd have to say, well, maybe then the rest is actually dark matter. So I'll throw up my conclusions here to just saying what I already said, and I'll take questions.
If you have any questions, just raise your hand. I'll come around with a microphone so those online can actually hear.
Okay, any questions for Craig? We got one
Here's
here.
one. Yeah.
So the Fermi, when it's gamma ray comes in, or how many times, or how much does it collect, or how many times does it detect a gamma ray? Is it consistently, or is it like one particle a year? Or
It's getting a lot. It gets a lot of gamma rays per year. So it has a wide angle for how it can study the sky. Let me back up to the Fermi. Here we go. Right. So it can collect them from a wide angle coming in, and it gets them fairly frequently. We have, so it can detect, for instance, enough gamma rays from an individual pulsar. Here, next one. Yes. Nope. Oh, it was the millisecond pulsars. There we go. Right. So you can see the total number of counts that it has from this millisecond pulsar, and this in number of bins. So this looks like it's, I don't know, maybe 500 or 1,000 counts that it has from this one pulsar, and that's a very small fraction of the total sky. So it's got, I want to say, many millions of photons from the sky, and keeps collecting at least hundreds of thousands every year, I think. It's not nearly as many as you get in the X-rays, say, because gamma rays are just fewer and farther between. But it gets lots. There's a question right here, I see.
I was wondering about the main calorimeter for it. Are you actually detecting changes in temperature Using something like that?
That's a great question. So that's this thing down here. I don't know exactly how the calorimeter on the Fermi actually catches how it actually calibrates the total amount of energy deposited. It might be in ionization or something else. There are calorimeters that we use in some X-ray detectors that actually the CRISM instrument is flying now. It's a Japanese instrument with US participation. That one actually detects temperature rise in a tiny little plate and then the temperature decaying, and they use that to measure the amount of energy in that individual X-ray. And other ones do the same kind of thing, but I don't know about the Fermi one.
We have a question online, so if that person online can just unmute their microphone, you can ask your question.
Well, I think you're inviting me to speak, so thank you very much. I'm Pete Jedicke from the London Center, and I don't think cataclysmic variables are the same thing as millisecond pulsars, but when you started talking about the statistics of how many of them there are in the Galactic Center, it sounded to me like either I got them mixed up or how many of them there each are, or if one's a subcategory of the other.
Right. Right. So we think that in the Galactic Center, there are lots and lots and lots of both of them, probably. So let me bounce back to the X-ray image of the Galactic Center. Here we go. So in this image here, you can see zillions of tiny little X-ray sources floating around. We think that the majority of these are probably cataclysmic variables, but there's probably a bunch of millisecond pulsars among them as well. And if I come to this plot here, you can see that among the brighter ones, there's kind of a separation between, so this is the observed ones in terms of their net counts. The brighter ones have some that show iron lines that are probably cataclysmic variables, and some that don't, which are probably millisecond pulsars and maybe some other things. So there's lots of each, probably tens of thousands of cataclysmic variables altogether, and probably if the explanation for these is being the source of the gamma rays as well, also tens of thousands of millisecond pulsars. There could even be millisecond pulsars and dark matter annihilation, just to confuse us. Nature sometimes does that.
Thanks. So can I follow up? So your graph shows the X-ray observations, and are those then lined up with the gamma ray observations, or are we talking about two separate data sets?
So the gamma rays don't have good angular resolution. So the gamma rays say there's a big blob of something that's producing gamma rays around the galactic center area. The X-rays have good angular resolution, so we can pinpoint individual objects. So we can identify these as a bunch of cataclysmic variables and likely millisecond pulsars that are around the galactic center area. And so it's quite plausible that these millisecond pulsars are what's producing the gamma rays. We're not 100% sure about that, but that's a plausible assertion.
Okay, thanks.
You're welcome.
Any other questions?
Yes, one.
Oh, count.
Yeah, thanks for the great talk. If you've got both cataclysmic variables and millisecond pulsars, I mean, the physics and the phenomena are totally different. Are we expecting to see that the millisecond pulsars will be fairly stable, only accumulating in time, whereas the cataclysmic variables, because they're throwing off material, might end up feeding the black hole or whatever black holes are nearby?
Oh, that's a great question. So you're basically asking, are one of these kinds of X-ray sources variable and the other one's not? Can we distinguish them in this way? And that's a great question. So the cataclysmic variables, well, their variable is in their name. They are likely to be variable because these are powered by a white dwarf carrying material from another star and that stuff falling onto the white dwarf. And so that intrinsically can be variable. So we expect them to be variable. So then you might think, should the millisecond pulsars be variable? And actually, there's another team that's tried to work on a similar kind of problem, and they made the assumption that all the millisecond pulsars would be stable. But I have a different view on that. And the reason is that, so if you look at the emission from a millisecond pulsar's surface, that will be stable with time. because there's nothing really changing dramatically on there. But those are the ones we're just looking at X-rays from the surface. Those are the ones that we can't even see at the distance of the galactic center. So there's two types that we can see. One of them, it's stuff in the magnetosphere producing really, really bright synchrotron radiation. Those should be stable except at the spin period, which it's hard to measure. But another group is the ones where it's a wind shocking between the companion star's wind and the pulsar wind. And those ones we know are variable with time. So I hold that just because an object is variable doesn't mean it can't be actually one of these millisekund pulsars. So I think it's quite likely that variable objects could be millisekund pulsars in here. So it's a great question, though.
Craig, got one last question over
Go
here.
for it.
In the Fermi telescope for detecting gamma rays, the gamma rays come and interact with the foil and create electrons and positrons. Does that limit the number of gamma rays you're able to detect? Only those that are able to interact via pair production? Are you missing out on a lot of gamma rays with that telescope?
I don't have a sense of how efficient the foil is at getting the. I think my impression is that the gamma rays are fairly likely to convert. They do have to pair produce. It is a pair production telescope. That's the way they detect gamma rays. If a gamma ray were to zoom right through there and not interact, then it wouldn't detect it at all. So I think it depends on the energy, but I think in the energy range that Fermi is designed for, it's fairly efficient at collecting them. So we do collect most of them that come in.
Thank you.
Okay, that's about how much time we got for tonight. So thank you, Craig. Very much appreciated. We have a round of applause for Craig and his presentation. Okay. Next up, we have the Observers Group update from either Murray Hunt or, there he is. Okay, there's an argument about who's going to do it. There you go.
Thanks, Clayton. See. Well, hello, everybody. I do have some images. We have some images tonight. It's been cloudy. I think a few of you have noticed for quite a while now. We were excited. Oh, okay, here we go. We have the monthly Zoom chat, as mentioned there. Next one, February 24th. And then we have in-person, short notice, in-town observing sites. We've got a few around the city, Sherwood Park and by the university. And we'll put out notices on the Edmonton website, the Astro list email. There'll be short notice because weather changes, and late in the afternoon of the day itself, we will either go or no go it. Could be any day of the week. Our last one was just last night. Our first one, I think, in January, February almost. Let me see. Okay, next slide, if we could. Okay, that was last night. We were overlooking the university farm. We had about 6 or 7 people out. As you can see, there's definitely lights. The lights are to our back. We were looking south-southwest. And we had quite a few interested people, and a few people who just walked by, stopped in, and a couple were quite knowledgeable about things. A few kids were out last night. Okay, next picture, please. Oh, one thing we did last night that I wanted to start with is I've been writing in the Stardust about some of the constellations, some of the main constellations, and Auriga, Taurus, Orion, of course, and I came across this idea of the winter circle, using those 8 bright stars: Capella, Aldebaran, Rigel, Sirius, Procyon, Pollux and Castor, back up to Auriga with Menkainen. Anyway, it takes up, as you can see, a large part of the sky. It was pretty well to our south, from Sirius low down to almost the zenith, Capella. And for me, after learning a number of constellations at least, I'm still learning how they all relate to each other. So here are 6 constellations. I kind of, as I see, something like a charm bracelet. 6 constellations. Each one is a charm, but they're all linked together in that one look. So that would be a nice unaided, naked eye observation. And as Alistair said different times, it's nice to, even 5 minutes, you have a little clear sky, go out and have a quick look. In one quick look, you can see main stars in those 6 constellations in the winter sky. Okay, next. And of course, the blaze star, D Corona Borealis. Well, we're still waiting. And there's Corona. Oh, let's see. There we go. I always like finding the brightest star first, but Bodhi's right here. And it's off the 6th star. If you see a star about there, if you see it visually, it's a blazing. Who knows? I was going out every night last summer, checking it. And then I read, well, it could be plus or minus 8-10 years. So I stopped looking. Oh, okay, next. That's the next slide. Oh, yeah. Dangerous ice. Ice can be dangerous at any time, slips and falls. And I forgot last night was particularly bad, but of course this whole week has been bad, just walking around. My daughter and her family came out for the first time last night, and actually my daughter fell and broke her arm. So just one more safety thing to be aware of, especially if you're going out of the city to a dark site. You're kind of alone if you're not with a group, and one slip and fall could be it. Crampons, some kind of spikes could be very useful. And then I don't know about liability if we're inviting people to come, but that's something to talk about next. That's it. Okay, I'm done. Okay, thanks.
Thank you, Mary. A reminder to look at our Astro email or Facebook coming up we have a total lunar eclipse coming up in the first week of March. And it's a, late night, early morning event, sort of ending at sunrise. Fingers crossed. We've had a lot of luck with clear skies with our lunar eclipses. And I'll just be posting some information on that coming up. So keep an eye out for that. And
Thanks.
Thank you. Okay. So just before the break, we'll go into the trivia questions really quick. And due to the fact that Artemis was supposed to launch on the weekend and didn't, I kind of went where it was a lunar theme. So first question is, who will fly the Artemis 2 mission? There are 4 astronauts. Okay, if they fly. What date did Apollo 17, which was the last Apollo mission to the moon, what date did it left the moon surface to head for home? And then how many people have walked on the moon? Now, if you're one of these conspiracy guys, nobody has. But we'll go with what NASA tells us. Okay, so we'll have our break. And then right after the break, we'll go and do the President's Awards. We have some announcements with Jeff Robertson and Dave Muscle around logistics. A couple other things as well. Then book of the month, Astro Imaging, trivia answers, and the final announcements. So we'll try to keep it to about 10 minutes and we'll go from there. Thank you. Okay. We'll do the President's Awards right now, and then we'll move on to some of the other announcements. So we came up with 5 awards this year. We have the George Moore's Memorial Award for Excellence in Public Education, Bryce Hartwell Memorial Award for Excellence in Astro Imaging, and we renamed this one to the Bruce McCurdy Award for Observer of the Year. And we got Franklin Lodi Award for Project of the Year, and then the President's Award for Service to the Center. So what we'll do, we'll start with the George Moore's Memorial Award for Excellence in Public Education. And I checked with Dave Muscle and verified that these 3 winners have been very active in the public outreach this year, this last year. And we would like to invite them to the podium. We have Stephen Portillo, Zaid Lorca, and Jan Kulak. Hey, I don't think Dan made it today, so if you guys come on over here and get together and. Great, thank you. Now, those 3 volunteered more than anybody else over the course of the year for public education, and they were well deserved. They did a lot of traveling around the province as well. Okay. I'll put Dan over here for now. Okay, Bryce Hartwell Memorial Award for Excellence in Astro Imaging. Went Tom and I and Jeff Roberts, Jay Lavender, we went through all of this, and since Tom had just done the top 10, he went through the last 10 years of the Astro Imaging Corner, and he came up with a name here that we have seen on Astro Imaging Corner quite a bit. He does quite a few images. He does provide at least 1 or 2 images every Astro Imaging Corner, and the excellence in his images are remarkable. So I'd like to thank and welcome Hans Jans to receive his.
Thank you.
Yeah, Dave, you got to take it.
Well.
Okay. Thank you, sir. Thank you, Hans. Okay, so we renamed the President's Award for Observer to Bruce McCurdy Award for Observer of the Year, which I thought was quite appropriate for the particular award. This year's observer did a lot of work getting the observing program back up and running for over last year. And as he indicated earlier, he's still doing quite well with that. And we want to thank Murray Hunt for being the observer of the year. There you go.
Thank you.
Geez, thank Murray.
Thank you very much.
Great work, Murray. Okay. Franklin Lodi Award for Project of the Year. Yeah, it took a little time to figure this one out, but 2 projects kept coming back to us. They kept saying, yeah, these are 2 good projects that we did over the course of 2025. So we decided to award both projects an award for it. And the first one was the library reorganization and cataloging. Mark Zalsik and Rosemary Bold did a great job in getting the library categories, get them the catalog, cleaned it up, made it very easy to use now, I'm hoping. And so I'd like to invite both those up to receive their award. Go on over here. So, hold your certificate. Thank Daisy. Thank you. Great work you guys did in the library. Okay. So the second project that came up over the course of our discussion was something called the Major Lunar Standstill of 2024-2025. And I think we saw the presentation a month or so ago when Alistair and Luca showed us the results of over 12 months of pretty heavy duty photography and imaging to get done. So I'd like to get Alistair and Luca up to accept the reward. Thank you.
Thank you.
Okay. Okay.
12 months? Felt like 12 years. Thank you.
Thanks again. That was also, just to let everybody know, it was also the Astro Imaging Photo of the Day APOD. So it's more than one person saw it, that's for sure. The last one is the President's Award for Service to the Center. This individual has done an amazing amount of work over the last few years running the Scope Loaner project. Not only did he keep the equipment up to date, kept it running, he also spent many hours handing out the equipment, helping people learn how to use it, and retrieving it at the end of the month if he could. So without further ado, and I'd like to thank James for all the hard work he's done for service to the center. So James McNeese. Thanks, James. You did a great job. Thank you. Great, thanks again. Okay. So I think all these people were well deserved in their awards, and we'll see what happens next year and when we go through these awards again. Okay, back to the announcement. Okay. Okay, we have some outreach opportunities that are still showing up on our logistics, but Dave Muscle has asked for a few minutes to go over the logistics program in case people are wondering how to use it, how to get on it. So Dave will be doing that, and Jeff Robertson will be speaking right after that on the same subject. So are you ready to go there, Dave?
Yeah, I am. Thanks, Clayton. I'm going to share my screen.
Yeah, we're seeing you.
Very good. Yeah, so I'm the volunteer coordinator, and between Jeff Robertson and I, we work together to ensure that events that members of the public call us about and are asking for support to do, like a sidewalk astronomy type experience for whoever is there. We are the ones who respond to that. Jeff takes the calls, and then I get the information. I create a schedule in our Volgistics system. And so the opportunity there is for the members who are signed up as volunteers. They can go into the system through something called VicNet, which is the front end of Volgistics as we know it. And that gives you the opportunity to examine the schedule, post your hours, and all that kind of stuff. What I wanted to do was just show you how simple this is. We have 81 volunteers who are registered who are registered in the system, and many of whom are involved. The majority of whom are actually involved in public outreach, and that's probably our biggest group and our busiest group. And so I'm just going to go to that screen here and just make sure I can access it here. Okay, so you should be seeing my VicNet screen. Is that what you can see on your screen as well?
Yeah, we're seeing that.
Okay, perfect. So once you've registered as a volunteer, you have access to this. And VicNet stands for the Volunteer Information Center Network. And So when you arrive at this spot, this you get to via the club's website. And if you remember, you can see the members area, and you can see within that a tab just for volunteers. This is on that tab. And so when you click on it, this is, you're looking at my profile here. And so the first thing you'll see are these titles here over on the left-hand side. One is the home screen. That's what you're seeing now. There's also a section for mail, and we occasionally send out email, but mostly people get a direct email or a text message in their whatever email system they're using. The other important module here is the schedule. And so this is what people check, and you would look up on this page here, and the default it's set to is the calendar view, but you can also see individual days. And then the last page, or the last tab that you click on, is the service page. And I'm going to skip this for now. I'm going to go back to the schedule and just show you what you see when you look there. And we have all of February. We've had several or 3 different events over February. One of which has happened and is behind us now, but one was canceled, and then we have one coming up on the 17th. And I think Jeff will speak to this. But if you click on that, it shows you what this looks like. And the information you get is that you get the time, you get the request. So this is for a presentation and an outdoor telescope tour at the Millwoods Sports Park Pavilion, and it gives you the address. And there's other information here as well. So from 7 until 9 p.m. Every event we get, we put in the schedule, and then this is what it looks like. And if you wanted to schedule yourself, if you're a volunteer and you are listed as a public outreach volunteer, you just click this green thing over here, and then you can schedule yourself in. You just click over here on Schedule Me. And if you do that, it'll change. It'll show your schedule now, which now includes this public outreach volunteer opportunity. And it'll also show the fact that there's still one more volunteer needed for this event. So I'll remove myself because I can't do this, but also this is something that anybody can do when they're here. If you change your mind about the involvement, then you can just simply remove yourself. We prefer that you don't. You follow through and you do the work that you thought you might be able to do. Very helpful that you do that. Anyway, I'm going to take myself out, and we're going to be back to 2 volunteers needed. Now, the next slide, or the next tab, is for the service tab. And so this is really mainly to encourage everybody who is a volunteer to use the functionality of Volgistics to record your time. And it's really simple to do. So for instance, today I've put in a few hours on the PlaneWave project. So I'm going to I'll stick 6 hours on that. And this is, you select the assignment. So in my case, I am assigned to a number of projects and responsibilities. One of them is the PlaneWave project. And I'm going to add some information here. I'm going to type in the fact that we worked on the camera and the computer. So that's a bit of a note that will remind you what you did. And just a couple more bits and pieces about this. The service data that you can put in here can be backdated all the way back to 1990, I think it is, in Volgistics. So if you can remember what things you've done over the years, you can put that in. But for the past couple of years, we've only been using this for 3 years now. And so we do have hours accumulated for a number of our volunteers from 2024, 2025, and now 2026. And you can do that. You can go back in the calendars and put in time, regardless of whether you have all the details. So just helpful if you do that. And it helps us actually track how much time goes to various responsibilities and assignments. And that's so that we can fairly and equitably assign the time and opportunities to the members who are standing up to be volunteers. So that's a very quick snapshot of how PicNet works. And I'm hoping that more of the volunteers that are currently in the system as registered volunteers use it. There's many that do, but there are some who, for various reasons, are not using it. And I've been getting questions about that. So that's the reason for this little tutorial. But if you are a person not registered in the system and would like to volunteer for the club, it's really simple to do that. Go back to the members area, and under the volunteers tab, the first thing you see there is access to the registration form. And that's a quick way to get information back to me and information to the system as to what things you'd like to be able to do for the club. And that allows me to enroll you in VicNet, and then you'll have access to the schedule and to the time recording and all the other functions of the system. And it's a very efficient system. It works well. It's used by a lot of other organizations, especially not-for-profit ones, because it's very cost effective. So that's my appeal to you, to use the system. If you are not registered, make sure you get that registration form into me, and I'll get you signed up with a password. And it's very simple to use as you've just seen. So back to you, Clayton.
Thank you, Dave. And now I think Jeff Robertson has a few words he'd like to say along this line as well.
Thanks, Dave. Excuse me for explaining that. It's the last event that I volunteered for that was listed on VicNet was on January 22nd. John Woolley and myself went to Michael Caustic's school for a telescope session. We had about 100 people there. We had beautiful clear skies. We looked at the moon. We looked at Jupiter, Orion Nebula, Saturn. We had a great time for about 2 hours. Oh, did I mention it was minus 26? This listing for February 17th for the junior forest wardens, they contacted us in August, and Dave put it up in September. So it's been on the list for 5 months, and nobody signed up. Now, I don't want to go back to them and say, nobody's coming. I can't come. I'm not even going to be here. I'm going to be on Vancouver Island that day. But I urge one or two people who can do a presentation for these people, talk about the sky, talk about stars. If the sky's clear, set up a telescope after and let them have a look at a few things. But with 80 volunteers, there's got to be one or two people that can come and do this. So I told my wife I was going to yell at the memberships, and I hope I'm not yelling, but please, we just need one or two people to do this for the 17th for the junior forest wardens. If you don't have a presentation, I've done a few myself. I can send you my presentations. They're kind of my style, and I cater them to the audience, but I could send you the PowerPoints and you can adapt them to whatever you can use if you want to do that. So that's all I got to say. Thanks.
Thanks, Jeff. So if anybody's interested in doing this particular outreach event, please get in there as soon as possible. Okay. As you can see, there's a scope loaner coordinator named Alistair Ling beside it. I only found out just shortly before the meeting started that Alistair, due to some issues that he had, he will not be able to step forward and take on that role. So that position is still open. So we're still looking for someone to fill that role. Same as vice president, we're still looking for someone there. And we don't need a national council rep because Alistair will continue doing that. Okay. So we got two other quick speakers we've got Luca got a little update on Black Nugget Lake Observatory, and Murray Paulson, who has something he'd like to share with us as well.
Thank you, Clayton. I just wanted to update the membership a little bit about Black Nugget Lake Observatory and seeing some of the observing reports from Murray and Alistair on the in-town observing. I just wanted to put a plug in for some dark sky observing. And so if you're doing in-town observing, you know the issues about light pollution and neighbors' lights shining, coming on with motion sensors just as you're getting a nice nebula in your telescope, or maybe you go to Blackfoot or some of the other places around town that lots of people go for observing, or even imaging, side of the road, Blackfoot, other places, and then you're kicking back, catching some photons for your next Astro Imaging Corner shot, and then a bunch of people show up to party, and laser pointers start going and things like that, and so there goes your dark adaptation, and maybe you lose some nice subs for your imaging project. So if you want a nice, dark, quiet place to observe or image with like-minded people and dedicated enthusiasts, I urge you to consider Black Nugget Lake Observatory. It's one of the crown jewels of our center. It's a dark site, far enough out of town to get dark skies, but not so far that it's terribly inconvenient to get to. It's easily accessed on paved roads. It's well equipped with nice amenities, and the center's 2 biggest telescopes are available to authorized members for visual observing. We have the 18-inch Barry Arnold Memorial Telescope with brand new coated optics, just come back from recoating. And of course, we also have Western Canada's largest telescope that members and the public can look through, which is the magnificent 32-inch Unique Drew telescope. As a dark site for astro imaging, it's a nice dark site to set up your rig. You need plug-in power? Got it. Need a warm-up room? Got it. Need a washroom? Got it. Right? It's all there. And you don't have to you never have to worry about white light trespass either. So there's 2 ways to get more involved and to get authorized to use the site. There's the user mode and the operator mode. If you just want access to a secure, dark site and bring your own gear, then become a user. If you want to get more involved and get access to the big scopes, then become an operator. The authorization process is straightforward and designed to ensure everybody's safety and to make sure that the facility and to ensure the facility's longevity. So I just urge you to consider to let BNLO be your window to the deep, dark night sky. If you want to know more, chat with me after the meeting or visit the BNLO tab in the members area. All instructions are there, and Galaxy season is approaching, and some big scopes are available for the membership to be able to look through or use. So I urge you to consider Black Nugget Lake. And I don't know, Frank, did you get the thing playing while I was talking? Okay. So Frank's going to show you, this is the last thing. I can't see anything. I'm just blinded by all these lights. So just installed this past month, we have an all-sky camera at Black Nugget Lake. And so you can watch the night sky through the all-sky camera if you wish, through live views during the night, plus archived time lapses that Frank will show you now. I can't see anything because I got some spotlights in my face. Can you see anything? Oh, there's Jupiter setting. Yeah. Okay. It's not as, oh, here. There we go. There's a live view right there. No. So anyway, there's an all-sky camera available, and it should just go to edmontonrasc.com/all-sky. And well, here's just going to show it on the computer screen. So there's a time lapse from, I believe this is a couple nights ago. There's also archived star trails and kiograms and things like that. So you just check out edmontonrasc.com/all-sky and you can see it. All right. Thank you very much.
Okay, Murray, he's got something of interest that we might be interested in. You can check with him after the meeting is over.
Yes, I came into possession of a chunk of the Edmonton iron meteorite. And so if anybody would like to see the Edmonton iron meteorite, stop by and see me after everything cools down here. Thanks.
it's a good sized piece of the meteorite, that's for sure. Okay, that should do it for the announcements for now. And if we can get back to the agenda here, if I can find it again. There, I did. Okay, book of the month. So, Frank, if you can bring up that page, I'll get Murray, Mark to talk about it.
Thank you. Good evening. And Rosemary and I thank you very much for the award. That's very kind. Thank you. The Kimball Library is open before and after the meetings, and we lend out books to members. What we've done over the past couple of months now is we've got surplus books sitting on the ledge there, which are free, but there's also a donation box if you would like to donate a small amount of money so we can purchase additional books. There's actually 3 titles on the ledge right now that have a price tag on them of the grand total of $5 each. If you'd be nice to pop $5 into the donation box, that'd be very nice. Thank you. Today's book of the month is actually one that's recommended in the Observer's Handbook. There's a page in the Observer's Handbook close to the front that has a list of recommended books, and this is one of them. It's a book on astrophotography, the 100 best astrophotography targets. And this is written on the back. Astronomical observing and photography are favorite pastimes of yours. You want to combine the two, but you're not sure how, or perhaps you have dabbled in astronomy for a while and want to take another step. What do you photograph? Will something that looks amazing as you peer at it through a telescope look the same in a photograph? There are so many dazzling sights in the night sky. How to choose? Ruben Keir has some answers for you. With his technical expertise and wide experience as both a visual observer and a photographer, he can help you attain some of the best images you can imagine, perhaps ones you will want to send to a magazine or proudly put up on your website. And the secret is it's not that hard. It's mostly a matter of choosing the right subjects and then doing the necessary post-processing to get results that will dazzle. So go out there on the next clear night and create something to show for your efforts. Your friends will be impressed, and you will be thrilled at how you're able to combine the two passions of your life into one. A neat aspect of this book is that they basically pinpointed one deep sky object and highlighted it for each day of the year. For example, coming up on Valentine's Day, February 14th, the feature, and each one has 2 pages dedicated to it, one of them showing an actual astrophotograph of that object. The one for February 14th is the Cone Nebula and Christmas tree cluster. What constellation is the Cone Nebula in? Any guesses? Monoceros. Very good. So, yeah, there's a little blurb on each object. For example, for this one, for imaging, they say that the region of the nebulosity around the Cone Nebula is vast. You can frame either a large region up to 3 by 2 degrees with a camera lens, or focus in on the cone with a smaller field. From the suburbs, an H alpha luminance reveals nice detail, but light pollution will drown out the faint blue reflection nebula. So that's just one object for 1 out of 365 objects in this book. So yeah, brand new acquisition, and it's available to lend out at the conclusion of the meeting. One other thing is the digitization of the library catalog is almost completed by Rosemary, and she says it'll be available as well within the next week or 2, as soon as that, perhaps. So that's almost finished as well. Great, thank you.
Thank you, Mark. Okay, Astro Imaging Corner with Tom Owen from way down south. So are you ready to go, Tom?
Yes, I am. I just have to stop the other person's screen sharing and I can get going.
Okay.
All right. So welcome to Astro Imaging Corner number 153. And without further ado, let's get going here. So this is the first image is from Al Pankratz. And he says that on January 31st, the moon's libration exposed Mare Australe, or the Southern Sea, an ancient impact basin that straddles the southeast limits of the moon. The impact that created the moon, or the basin, is estimated to have hit the moon during the pre-Nectarian era, 3.9 to 4.5 billion years ago. And in the hundreds of millions of years following the initial impact, the basin was peppered with numerous subsequent craters that largely obliterated its features. In turn, some of those craters were modified when lava welled up inside and around them. As a result, Mare Australia has a modeled and chaotic appearance, more modeled and chaotic appearance than the more uniform basins on the visible side of the moon. My apologies. The first image shows the region of interest framed in red. It was taken with a 10-inch f6 Newtonian, a Canon R6 camera, and a 2x power mate. The second image shows a zoomed-in view of Mare Australis and was taken with the same telescope and camera, but with a 4x power mate. It's an interesting challenge to see how far around the mean limb of the moon it is still possible to pick out features. Extreme foreshortening makes positive identification difficult, but using satellite images and lunar charts, it appears that the lava-filled crater Jeans N is just visible. See the label. Jeans N is centered at lunar longitude 58.55 and then 90.6 E. These images were lightly enhanced with Affinity Photo 2. And I really like these photos, in part because this kind of activity, looking or observing or photographing the libation of the moon, seems to me this is a link to members' activities at the center, probably going back to the formation of the center in the 30s. And so I think it's just a great tradition and a continuation, and it's a thing that members of astronomy clubs should be doing. All right. This is from Alan Hobbs, who I should add is was the 2023 Astro Imaging awardee. And this is, of course, the Horsehead Nebula. And he says, the Horsehead Nebula is a small dark nebula located about 1,375 light years from Earth in the constellation of Orion. The nebula is located just to the south of Alnitak, the easternmost star of Orion's belt, and is part of the much larger Orion Molecular Cloud Complex. Marion and I were visiting Dave and Carol Mussel on the 18th of January this year. I set up my C-Star S50 in equatorial mode using a Skywatcher wedge on a photo tripod and shot the Horsehead Nebula, 105 subs at 20 seconds each for a total exposure time of 35 minutes. I processed this astrophoto in PixInsight from the stacked FITS file. And this is his image of the Helix Nebula. He says, the Helix Nebula is a planetary nebula located in the constellation Aquarius, discovered by Carl Ludwig Harding, most likely before 1824. This object is one of the closest of all the bright planetary nebula. The distance measured by the Gaia mission is 655 plus or minus 13 light years. The Helix Nebula has sometimes been referred to as the Eye of God. And he says, on November 22nd at Lake Tekapo, New Zealand, with my C-Star S50 in equatorial mode, using a Skywatcher wedge on the C-Star tripod, I centered the C-Star on the Helix Nebula with 63 stacked subs of 20-second exposures, total of 21 minutes exposure time. I process this astrophoto in PixInsight from the stacked fits file. And of the small Magellanic Cloud, Alan writes, this is a dwarf galaxy near the Milky Way, classified as a dwarf irregular galaxy. The SMC has a D26 isophotal diameter of about 5.8 kiloparsecs, 18,900 light years, and contains several hundred million stars. There's a total mass of approximately 7 billion solar masses at a distance of about 200,000 light years. The SMC is among the nearest intergalactic neighbors of the Milky Way. It's one of the most distant objects visible to the naked eye. On November 16th at Kaikoura, New Zealand, with my Seastar S50 in equatorial mode, using a Skywatcher wedge on the Seastar tripod, 73 stacked subs of 20-second exposures, total of 24 minutes and 20 seconds exposure time. I processed this astrophoto in PixInsight and Photoshop from the stacked fits file. So all you Seastar users out there, this is kind of what you can do. And it shows that it's not the skate, it's the foot in it. So I want to see more Seastar images. Thank you very much. So from Hans, we are 2025 award winner. We have the supermoon. He says this is as taken from Bortle 7/8. All of these images, and there'll be a few of them, were taken from Bortle 7/8 skies in Sherwood Park with a ZWO ASI 2600 MC Pro camera. And the image acquisitions were controlled by Nina, and images were processed in PixInsight. So he says the supermoon on November 4th last year was taken with Teleview NP127IS, combining a total of 110 exposures of 1 millisecond each. I found that astroperic turbulence can be counteracted quite effectively with a deformable registration algorithm and open source software called Elastics, which warps all frames slightly to conform to the highest quality. We really like mineral supermoons at Astro Imaging Corner, so well done. So this is, of course, M15, the bright globular cluster in Pegasus. And he says it was only intended as a filler while waiting for the next target to rise later at night, but it turned out reasonably well with only 90 minutes exposure time. Telescope, again, was the Teleview NP127IS with a native focal length of 660 millimeters at f/2. And this is LBN 576, aka the Garlic Nebula. It's a supernova remnant about the size of the full moon in the constellation Cassiopeia. Its visual magnitude is around 15, so it is fairly faint and requires 16 hours of exposure with an HA03 dual narrowband filter. The telescope was an Edge HD 9.25 inch with a 9.25 inch with a 0.7x reducer for a focal length of 650 millimeters at f/7. And this is SH2124, an emission nebula in Cygnus and surrounding nebulosity. This is in the Hubble palette, in which elemental emissions from S2, H alpha, and O3 are mapped to red/green/blue, respectively. The actual sharpless object is the small circular structure to the right of center. The image acquisition time for this was about 22.5 hours, with dual narrowband filters, HA/O3 and S2/O3, and 1.5 hours in RGB to capture the stars in their natural colors. Telescope was again the NP-127IS, equipped with its 0.8x reducer for a focal length of 520 millimeters at f4.2. So, Hans, I saw that he joined the center in 2021 and at some point started submitting images, and it was kind of like Athena springing fully formed from the head of Zeus. They were excellent right from the beginning, and they have continued to be excellent. And it's for that continued excellence that we wanted to give him the Bryce Hartwell Memorial Award in Astro Imaging. So I want to add my congratulations. This is Hans's last image, the Triangulum Galaxy. And he said that he acquired 37 hours of data in RGB and 7 hours with an HA03 dual narrowband filter to bring out the galaxy's red H-alpha regions in which new stars are being formed. The telescope was the NP-127IS, equipped with its 0.8 reducer, again for a focal length of 520 millimeters at f4.2. And the Triangulum Galaxy is a difficult subject, and I think he did an outstanding job here, particularly highlighting the HA. So, again, I would ask everybody to send your images to Astro Imaging Corner. Obviously, we've had a bunch of cloudy skies, but I think you'll be happy that I'm down here in Bucerias because I brought the cloudy skies with me and taken them away from you, so you can thank me later. So we've had I've been monitoring the situation. It looks like we've had some clear skies. I look forward to receiving lots and lots of images for the next edition of Astro Imaging Corner. So, adios.
Thank you, Tom. There were some amazing images for this particular edition. So, okay. We'll get to the trivia answers here real quick. Okay, so who will fly the Artemis 2 mission? We have Reed Wiseman, who's commander. Victor Glover is the pilot. Christina Cott is the one mission specialist, and our own Canadian Jeremy Hansen is the second mission specialist. What date did Apollo 17 return to Earth? It left the lunar surface on December 19th, 1972. And how many people have walked on the moon, according to NASA, is 12. And only 1 or 2 are still alive, if I remember right. Okay, final announcement. Take a look at that cartoon of the month. Oh, there it is. Okay. No, a waxing moon does not have anything to do with hair removal. Okay. So go back to that last page there. Next meeting is Monday, March the 9th, pardon me. Oh, I gotta fix those things. March the 9th, 7:30 Mountain Standard Time. Also, Telephoto Science will be doing a Artemis watch party. You're gonna have a launch party. I think the next date that I saw was March the 8th was a tentative date for the
March 6th. March 6th will be the next possible earliest date, I think.
Okay. But as we know from NASA's previous ability to launch on time, that could change anytime. So anyway, so keep an eye out on the TU's website for any more information on the launch. And when they do have it, we will have a RASC table set up in the lobby to talk to the public about the RASC. So next Monday, March the 9th, will be the next meeting, and we look forward to seeing you then. Otherwise, stop by and see Murray about the meteorite. That's it for now. Thank you very much.
Wait, can I just say a couple of things? First off, it's Frank again over here.
Yeah, sure, Frank.
Just March 3rd in the morning. That's the lunar eclipse that, again, Alistair kind of mentioned a bit. If anyone does want to come out to the Telus School of Science Edmonton, to the RASC Observatory, I'll be here. I don't know how many public to expect, since it only starts around after 2 in the morning or so for the umbral eclipse. Goes to about 6:30, I guess, and then the moon sets later. But if anyone does want to come out and bring a telescope, if the weather's good, I'll be here. We'll be sending out a press release, of course, and hopefully we'll get a few public that might be able to make it out on that Tuesday morning, really, really early. So if you do have a chance and want to come on out, help us out with whoever might be here, or just come out to the observatory and keep me and maybe a few others company, please do. I'll try to maybe get some coffee for everybody or whatever you might like to drink. So thanks. Sorry about that.
No problem. Thanks, Frank. Okay. Without further ado, we'll adjourn the meeting for February. Thank you.